am Afrazi, and today we are going to explore a very important topic of mathematics, calculus. Imagine measuring the instantaneous speed of a car. It is very difficult using algebra, but by using calculus we can find it very easily. To find the speed of a car, we have to first measure the slope. Let us see how to measure the slope of a curve. Now, we know that the slope of a straight line is defined as the ratio of the rise to the run. Now, rise is the change in y coordinate, whereas the run is the change in the x coordinate. The slope can be found out by y2 minus y1 divided by x2 minus x1. Here, if it is point x1 and y1 and point x2 and y2. Now, if this is the rise and this is the fall, the ratio is called as the slope. But the slope of a line is not very interesting. Imagine if the line is not a straight line but a curve. Here, to find the slope of a line x1 and y1, we have to draw a secant line. Then we can find the slope of the given line. Now, formula will be the same. To find the slope of these 2 points x1 y1 and x2 y2, we have to use the same formula, y2 minus y1 divided by x2 minus x1. The formula still gives us the slope of the second line, showing the average change between our 2 points. Now, suppose if the curve is like this. Instead of any 2 random points, let's start at a point x here and then move to a specific distance h. If this point is x, then this point will be x plus h. Now, we have to find the slope. If we change the value of x, the value of y will be f of x. And if for x it is f of x, for x plus h it will be f of x plus h. Now, if y2 will be f of x plus h, y1 will be f of x. x2 is x plus h and x1 is x. Now, f of x plus h minus f of x divided by x plus h minus x. The positive x and the negative x gets cancelled and the equation comes out to be f of x plus h minus f of x upon h. This is a very basic fundamental principle of calculus. This can also be called as the engine of the calculus. Now, let us see. Here the value of h is large. If you gradually reduce the value of h, the slope also changes. At one point, the second line will be converted into a tangent line. This is the instantaneous rate of change. As we reduce the value of h, the second line gets converted into a tangent line. So, the f of x plus h minus f upon h, this was the basic fundamental formula. Now, the value of h as we reduces it becomes nearly equal to 0. We say that it approaches 0. So, we apply the limit as h approaches to 0. Why don't we say that h is equal to 0? If h becomes equal to 0, the whole equation will not be defined at any instant in algebra. So, what we do that is we say that f approaches 0. This is the magic of calculus. We write the limit as h approaches 0. It is a mathematical way of asking what happens if we get infinitely close to 0 without actually breaking the rules of algebra. Now, so first we have seen the slope of the straight line. Then we have seen the slope of the curve. We have selected 2 points and found the slope of the second line, and as we needed at least 2 distinct points for that, and what we find at that point is the slope is the average rate of change, whereas in a tangent line we get the instantaneous rate of change. Algebra is tracked between 2 parts. Calculus allows us to freeze time and measure a single instant. Now, let us give a live example for that. Consider the equation f of x is equal to x square. Now, if we apply the limit, if we have substituted the formula in the first principle of calculus, if limit as h approaches 0, f of x plus h minus f of x over h. Now if we substitute the value of f of x, f of x becomes x square, and f of x plus h becomes x plus h whole square. So the current state becomes limit as h approaches 0, x plus h whole square minus x square over h. Now if we have find the algebraic identity a plus b whole square, which is a square plus 2ab plus b square. So it becomes x square plus 2hx plus h square minus x square as it is divided by h as it is. This positive x square and negative x square gets cancelled. It comes out to be 2hx plus h square upon h. Taking h common, we get 2x plus h upon h. H gets cancelled out and the answer comes out to be 2x plus h. This is the part. Now, what was the limit as h approaches 0? Now, as h has been cancelled, there is no denominator there. We can directly substitute the value of h as 0. So, it becomes 2x plus 0, which is equal to 2x. We can say that this is f dash of x, f prime of x. This means the derivative of x square is 2x. The slope of the tangent line anywhere on the line is simply 2x. So if we, for any, the slope of line at any point on this curve, if you draw the tangent, we will get the answer to be as 2x. Now let us solve the first question. We have to find the slope of the curve at x equal to 1. Now what we have here is, the formula is, for value of slope is 2x, as this is x square, the formula is 2x. What we have to do is, we have to replace x by 1 as it is at x is equal to 1. So 2 into 1 is 2. The slope of this curve at x equal to 1 is 2. This is how we solve calculus problems. Now, what we have done here in this presentation, what we have done is we have found out the instantaneous change. By finding out the instantaneous change, we found that we cannot divide by 0. So what we did was, we algebraically substituted the values such that h cancels out and we get the answer. Calculus is the art of setting up an impossible scenario. Given here is the measuring the change at 0 distance. We have measured the change at 0 distance using a limit to define boundary and using algebra to cheat the division by 0 rule. We have found the rate of change of a sine wave, which came out to be cos x. Now we have to find the rate of change of a cosine wave or cos wave. Here, that is f of x will be cos x. So f of x plus h, it will be cos of x plus h. Substituting these values into the first principle, we get limit as h approaches 0, cos of x plus h minus cos x upon h. Now, the limit is h approaches 0, cos of x plus h minus cos x upon h. We know that cos of x plus y is cos x cos y minus sin x sin y. So, replacing this cos of x plus h using this formula, we will get limit as h approaches 0, cos x cos h minus sin x sin h minus cos x upon h as it is. There is no change in that. So cos x cos h minus sin x sin h minus cos x. This is the numerator. From the first term and the third term, we are taking cos x common. If we take cos x common, here cos h minus cos x taking common, it is 1 minus sin x sin h as it is. So this is the numerator of the function. So it becomes limit as h approaches 0, cos x cos h minus 1 minus sin x sin h upon h. Now this limit can be divided into two parts. First, in the term cos h minus 1, and second sin x sin h. First, dividing h over both the terms, the limit here h approaches 0. So the cos x can be taken out of the limit. Similarly, sin x also can be taken out of the limit. So the two limits becomes cos x times limit as h approaches 0, cos h minus 1 upon h, minus sin x times limit as h approaches 0, sin h upon h. Now there are two limits here, cos h minus 1 upon h and sin h upon h. This is a known standard limit whose value is 1. Now let us find the limit of this function cos h minus 1 upon h. So limit as h tends to 0, cos h minus 1 upon h. First multiply and divide by cos h plus 1. Now what we will get is cos h minus 1 cos h plus 1 upon h into cos h plus 1. Now a minus b into a plus b. This is the algebraic identity. A minus b into a plus b is a square minus b square. So cos h minus 1 into cos h plus 1 becomes cos square h minus 1. So the limit becomes limit as h approaches 0, cos square h minus 1 upon h times cos h plus 1. The denominator as it is. Now cos square h minus 1, it is minus sin square h. The trigonometric identity is cos square x plus sin square x is 1. So cos square h minus 1 becomes minus times sin square h. So the limit becomes limit as h approaches 0, negative sin square h divided by h times cos h plus 1. Now separating it again, sin h upon h, sin square h, in sin square we are writing as sin multiplied by sin. So sin h upon h, sin h upon cos h plus 1. We are dividing into two parts. So limit as h approaches 0, sin h upon h into negative sin h upon cos h plus 1. This is again the standard value. Limit as h approaches 0, sin h upon h, its value is 1. Now if we substitute the value of h as 0, sin 0 is 0, cos 0 is 1. So it will be 0 upon 1 plus 1. This value is 1 multiplied by this value is 0. 1 multiplied by 0 is 0. So the first limit became as 0. Cos x into 0 minus sin x into the standard limit 1. So 0 minus sin x into 1, which is minus sin x. So by the limit definition, the derivative of cos x is negative sin x, or we can say that the rate of change of cos x is negative sin x. We have found the rate of change of a quadratic function. Now let us move on to some trigonometric functions. The first is sine of x. Now what our goal is to find the f dash of x, that is the rate of change of x for the function sine x. Now we can do this by using the first principle, where what is given by f dash of x is equal to limit as h approaches 0, f of x plus h minus f of x upon h. This definition requires for us to evaluate our function at x and at an infinitesimally small step forward x plus h. Now substituting the values, f dash of x is equal to limit as h approaches 0, sine of x plus h minus sine x over h. Now what we'll do is we'll use this formula, sine of a plus b, which is equal to sine a cos b plus cos a sine b. We will simply substitute sine of x plus h by this formula. What we will get is limit as h approaches 0, sine x cos h, sine h cos x. We have used the formula sine of a plus b, which is equal to sine a cos b plus cos a sine b, minus sine x as it is over h. We have used this formula. Next, now sine x we have taken as common. So here in these two terms, sine x plus h, sine x cos h and sine x, we have taken sine x common. If we remove the sine x, here it is cos h minus 1. So limit as h approaches 0, sin x common, cos h minus 1 plus sin h cos x as it is upon x. Now, we are using the fraction properties. A plus b upon c is equal to a upon c plus b upon c. We are distributing the h over this. Sin x cos h minus 1 upon h plus sin h cos x upon h. We have distributed h over both the terms. Now, as the limit is for h approaches 0, we can remove the sin x from the limit function. Similarly, we can remove the cos x from the limit function. So the equation becomes sin x times limit h approaches 0 cos h minus 1 upon h plus cos x times limit h approaches 0 sin h upon h. Now, what we have here is limit. This is a standard limit identity. Cos h minus 1 upon h, limit as h approaches 0 is 0, and limit as h approaches 0 sin h upon h is 1. So by replacing these values, so this value becomes 0, sin x times 0 plus cos x times 1. Sin x into 0 is 0, cos x into 1 is cos x. The entire function becomes cos x. So d by dx, or change in the sine function, is equal to cos x. Through the first principle, limit definition, trigonometric expansion and fundamental limit identities, we prove that the exact rate of change of a sine wave is perfectly described by a cosine wave. Thank you.